Welcome everybody today afternoon for this seminar on transiting exoplanets in PLATO. And I would like to give you an overview of the transit methods, what's done with transiting planets these days, where are we, in particular in terms of small and rocky planets, and in particular, of course, what the PLATO mission will tell us. This is in the context of astrobiology. So I made a list of some main points that affect the planetary habitability, so the capability of a planet to host life. And one of the most important parameters is the location of the planet in the habitable zone. You see on the right the illustration of the habitable zone being the distance from the star, where a planet like our Earth is just right in temperature, which means it can host, it can have liquid water on its surface for long periods, because we believe we need liquid water to form life. When we move our Earth too close to the sun, all the water will evaporate and be lost to space. And when we move the Earth away from the sun, the water will freeze out and we have a frozen planet. So these are the limits of the habitable zone. And what we are looking for in our field of exoplanets are, of course, the first thing we're looking for is to have a planet that's just at the right distance. The next point is the system architecture. Architecture means, are there more planets in the same system? Are they in the same order as in our solar system? So the rocky planets inside and the gaseous planets outside. And what is the stability of the system? Because, of course, that affects the climate conditions on the planet. The planet itself should be a rocky planet, so we need to know the mass, radius, the mean density, and the gravity, but also its interior structure is important, because planetary atmospheres are outgassed from the interior for rocky planets, so we need to know what is the interior structure, and is such outgassing probable for this particular planet. And finally, the atmospheric composition, the long-term climate, stable climate, and shielding of the atmosphere are important parameters we need to assess habitability. Finally, if there's life, we can only find out if we have the biosignatures, but I'm not talking about biosignatures today. In addition to the planet itself, we also need to know about the star, because the stellar properties, of course, affect the planet. The star is the source of the energy. The star evolves with time and will impact the planet as well. So here in this list, I highlighted in blue what the things we could measure, the things that we can determine. And you see what we can determine are very simple things. The complex issues like interior structure, outgassing, climate stabilization are things we have to infer from the few measurements that we have for extrasolar planets. Today, I will focus myself on the transit methods, on so planets detected or observed showing transits. And this little movie from NASA just shows the idea behind that. With the transit method, we can detect planetary systems that we see edge on. So in regular intervals, the planet will pass in front of the star, as seen from us, causing a dip in the light curve of the star. That means while the planet is in front of the star, it blocks light of the stellar surface and the star appears fainter. And the magnitude of this dip is proportional to the planet cross-section over the stellar cross-section. That means if we know the size of the star, we can infer from the measurement of this dip, of the blocking of light, we can infer from this the radius of the planet. Among all the detection methods we have today, this is the only method which allows us to measure the radius of a planet directly. It's getting even more interesting if we can compare if we can combine transiting planets with other detection methods. So here you see some illustrations in the top row. You see again the transit methods and the diminishing of the stellar brightness when the planet passes through the line of sight. And next to it, we see an illustration of the so-called radial-velocity method. The radial-velocity method is a spectroscopic method, and it measures the motion of the star, which is induced by the planet orbiting the star. Both together orbit around the common center of mass, and so when we can measure the motion of the star, we can infer the orbital period of the planet. We can also determine the masses of the planet. And in fact, when you make a list of the things that we can learn from transiting planets, from photometric measurements, so intensity measurements and spectroscopic measurements, the list is quite long. It's not only the orbit, the radius, and the mass. They together give us the mean density, but for planets close to the star, we can also determine phase curves and the albedo, the reflectivity, the temperature, love numbers, which are give a handle on the interior mass concentration, although this is possible today only for gas planets, but still. And the Rossiter-McLaughlin effect from radial velocities, which gives us the star-planet spin orbit alignment. And even more, while the planet is in front of the star, we can perform transit spectroscopy. That means we observe during the transit, we see the stellar light shining through the atmosphere of the planet to us. So or when the planet is going behind the star, we can, in the infrared, detect emission spectra, some emission spectra from the planet. And that allows us to determine atmospheric composition. And the infrared also gives us temperature and also to constrain atmospheric loss processes. So altogether, you see a relatively long list of parameters we can infer from transiting planets, and that easily explains why transiting planets are in the moment in the focus of in the research field. And that is also reflected if you look at the statistics of exoplanet detection over the years since the mid-90s. You see the purple color in this histogram marks the transiting planets. And this is today really the dominant detection method, not only because we have these, the various space projects going on, but also this is not by chance. It's really because we can learn so much about transiting planets. When we look at the exoplanet detection status, then in one way or another, we always see this plot, which plots the mass of planets in here over the semi-major axis. I've put in this plot the pictures of our solar system to give you an orientation, and the colors indicate the various detection methods. Violet is the transit method. You see the transit method appears up here. It has a strong bias to close-in planets, but as we will see, today's cutting-edge detection methods, we want to push this detection limit out to 1 astronomical unit. We'll come to that later. When you look at this diagram, it's actually quite interesting because we see the upper left part of the diagram, which is full of dots detected by various methods, and then we see the lower right of the plot, which is empty. And that's not because there are really no planets like our solar system. It's simply because this parameter range is not accessible yet, and we don't have the means to detect the planets there yet. In the populated part of the diagram, we also see the planets are not uniformly distributed, but we see gaseous planets, hot Jupiter planets. We see at the place in the diagram where we have less Jupiter planets at certain semi-major axes, and then we have many planets again, which are like Jupiter in our solar system. And what is most interesting, what was most exciting in exoplanet research over the last years was the detection of many planets which are in between the mass range of Earth and Uranus, Neptune in our solar system. We don't have planets like this here, so we don't have any detailed analysis of such kind of planets, and they in the moment provide the largest challenge to understand what are these planets like. If you look at the detection numbers, we have more than 6,000 planets known today, but out of these, almost 2,000 have a mass and a radius measured, but only between 205 and 300 have a parameter range where we say, okay, they could be rocky planets, so below less than 10 Earth masses, less than 2 Earth radii, Earth or super Earth planets. So in terms of astrobiology habitability, the number of known rocky planets is actually very, very small. The first handle to learn about the nature of a planet is the mean density. And in 2015, Atihatzis and I made this diagram just empirically plotting the mean densities known at the time versus the mass of planets. And it turns out this gives this kind of zigzag curve. In the right hand, the red dots, you see these are stars. So the planets have hydrogen burning, and the larger the mass, the stars just get denser and denser inside, so the density goes down. But if we stay in the range of the planets, from low mass to giant planets, we see this curve gives a kind of V shape, and the right branch here are the gaseous planets, and in the left branch we have the Uranus-Neptune-like and rocky planets. There are sketches in here which how these planets could look like from the interior. And you notice there's a lot of scatter in the density. There are a lot of different interpretations how these planets could look like. And this is a mess. We have to understand this better and find out what are these planets and what is their nature and which ones could be habitable. But so mean density is a good parameter for planets to really, for the big picture. Yeah, to see am I on the right branch or am I on the left branch, but then it's difficult to address in particularly super Earth mini Neptune planets. And that is definitely true. The challenge here really is to constrain the planet interior. If you assume the planet has a core, it has a mantle, it could have an ice or ocean layer, and on top an atmospheric gas layer. With a 4-layer model like this one, and a parameter range between Earth and Neptune-like planets, it is very tricky to really find out how is the interior structure because there are degeneracies. And there are even degeneracies if you look at the rocky planet like in the famous TRAPPIST-1 system. You can have for the same mass and radius, you can fit models with no core, fit models with a mantle and a core, and models which have an ocean on top as an outer layer. So we know that mass and radius alone are not enough to resolve these degeneracies in the interior modeling. However, if you don't have a precise radius and mass, it's impossible to even constrain the interior structure. And this was has actually led to some research because we were building PLATO to get precise radii and masses. So how precise do you actually have to be? And one example of the studies that have addressed this here is from Philipp Baumeister and Nicolas Tusi. What they have done forward modeling of thousands of planets of various types, and then performed some machine learning a method to retrieve the interior structure distribution from this simulated ensemble of planets. And I'm showing you here an example. This is a planet with 1 Earth mass and 10% uncertainty in the Earth mass, or 1 Earth mass, and 1 Earth radius, so really an Earth twin. And the what has been varied here and coded in the color graph is the uncertainty of the radius. I assume I have a 1 Earth mass planet, and I measure the radius with certain uncertainties, measurement uncertainties. And you can see here that with 20% radius uncertainty, we can't say anything about the size of the core and the mantle in this planet. And only with 5% uncertainty in the radius, we are starting to be able to constrain the core size for such a planet. And that told us we really need to have precise radii measurements, at least 5%, and 10% in masses. So of course, there have been more complex model variations done following this initial study, but they came to the same conclusion. We really need the radii and masses with a certain precision. And an example what you can do with this information later on, an example I like, of course there are many, but this one I choose is GJ367b. GJ367b is orbiting not a solar-like star, it's orbiting an M dwarf star, which means the star is smaller, so we can detect smaller planets around a smaller star. And here we have a planet which is half the size, no, 70% of the size of Earth, but half the mass of Earth. So really a small planet. The mean density is clearly in the rocky regime. And this simplifies it because with such a planet, one can assume that the atmosphere gaseous layer is probably small. And then you can say, okay, probably it's a rocky, it's a terrestrial-like planet. And then here you see the result of such a retrieval algorithm, which says that this planet, about 90% of this planet is actually core. And that reminds us, of course, to Mercury in our own solar system. So this kind of planet seems to be a kind of super Mercury, a planet with a large core. And meanwhile, we know it's an own class of planets, these ultra short period planets with large rocky cores. And we need to find explanations for these planets, for the formation of these planets in future. So that's this kind of work we would like to do, of course, with many, many more planets with precise constraints, at least on the observables where we can have that. So why don't we have more planets with a measured mass and a radius? Why are we in this situation? Well, that's actually a point of the various detection methods, the sensitivity of the methods and the sensitivity of the instruments that have been used in the past. The radial velocity method in this histogram, which shows the number of detected planets versus the optical magnitude of the stars. So fainter stars are on the right and brighter stars are on the left. It's the magnitude system. So the radial velocity is sensitive. These are these brownish colors. So we have a peak at 8 magnitude, and the sensitivity goes down to 8, 10, 11 magnitude range, which is good for radial velocity. But the Kepler mission, the mission that recently produced most of the planets and planet candidates that we have today, the Kepler mission had a peak in 14, 15 magnitude. And only few Kepler targets were bright enough so they overlapped with the magnitude regime where we can get the masses. Yeah, so Kepler detected many, many planet candidates. It could measure the radii very precisely, but the stars were too faint to get masses from the ground. That's simply what it is. So from this, the message was very, very clear. Kepler was a great mission, but we need to detect planets in a magnitude range which has a larger overlap with the radial velocity method. And that is actually what is done. So if you look at the history of transiting method of space missions, the whole thing started with Kourou. Kourou was a small satellite led by the French space agency CNES, together with a few European countries and ESA, orbiting until 2012. And the big milestone of Kourou was the first detection of a rocky planet outside the Earth. This was Kourou 7b, 2 times the size of Earth, but an orbital period of only 20 hours. So in terms of astrobiology and habitability, definitely not habitable, but it was the first one of its kind. Then Kepler came, and Kepler gave us statistics. Yeah? It told us that every second star has a planet. It told us that mini Neptune super-Earth planets are more abundant than gas giant, these hot gas giant planets, and gave us statistics, but not in terms of characterization as I've just shown. Now, TESS took the lessons learned from the message of the magnitude range. TESS is observing brighter stars. The TESS mission is still in operation. and it's performing target statistic on bright stars, which are sufficient for characterization. But TESS is scanning the whole sky, so really large numbers of target stars, but scanning the whole sky, and therefore focuses on planets with orbital periods up to 100 days only. It doesn't cover the habitable zone of a solar-like star. The other mission still in operation, oops, sorry for that. The other mission still in operation is CHEOPS from ESA. CHEOPS is not a detection mission. CHEOPS addresses the point of precise characterization, so CHEOPS determines precise radii for known planets. The question then is, what is the next step? And then where we have to go in terms of parameter range is very, very clear. To the left, here we show the plot, plotting the stellar mass of the host stars of planetary systems versus the semi-major axis of the planets. 1 means we have a solar-like star. The green band is the habitable zone, the position of the habitable zone. And we see the green band moves to the left. That means the green band, the habitable zone, moves closer to the star for smaller and cooler host stars. All these dots in the diagram are known extrasolar planets up to 15 Earth masses. And now to the right, we have the same plot, the same parameter range, but we limit the precision, required precision to the one we need to infer the interior structure of planets. And then you see the whole plot looks rather empty. In the habitable zone of solar-like stars, we only have these triangles. This is our solar system. And then we have examples here in the as planets around dwarf stars. But we don't know, we really don't have well-characterized rocky planets in the habitable zone of solar-like stars today. And I've shown the versions of this plot 15 years ago when we were presenting PLATO, and it hasn't been filled. It will not be filled before we fly PLATO. And that's clearly, that's clearly where the PLATO mission will go. So what is PLATO? PLATO is then ESA's next mid-M-class space mission, M3, in the Cosmic Vision program. The goal of PLATO is to detect by the transit method and to characterize for the radius, mass, and age, exoplanets, including, and in particular, of course, the small planets in the habitable zone of solar-like stars, filling the gap that we have today in our knowledge about planets. We want to launch in spring next year, so everything is fine so far for spring next year. PLATO has a pretty peculiar design for a telescope. It doesn't have the single dish design that you're maybe used to for telescopes. Instead, it has 26 individual cameras. Each camera has a small aperture, only 12 centimeters each. But altogether, these cameras first provide a very wide field of view, almost 50 by 50 degrees. That's needed to get enough stars to observe transits. And at the same time, we get a large, what we call a dynamical range, which means we can get high precision photometry on bright stars up to 4th magnitude, and on fainter stars down to 11 or 13th, even 13th magnitude. And this can be done for the brightest stars. One of these cameras is enough. For the faintest stars, we co-add the light of several cameras. So PLATO will operate for 4 years. That's the standard operation time given to a mission by ESA. During these 4 years, the baseline planning is to observe 2 target fields for 2 years each. However, the satellite itself has consumables for more than 8 years, and that means if we convince ESA to get that the mission is doing great science, we can extend the mission and double the observing baseline, which is important in particular, of course, for the long period planets. And I have here 2 pictures just to show you it's real. The upper left is actually an engineering model, but I find it a bit nicer a picture to see the satellite and get a handle. Here, where you see the cameras without a lid. we see the satellite in the big thermal vacuum tank at ESA doing its final tests. So just a word on the quick work on the spacecraft. To the left, we see that we have the cameras. They're sitting on the optical bench, sitting on the satellite platform, which shows onboard computers, power supply, and so on. All of this is covered by a sun shield. And the satellite will launch, as I said, in spring next year. It will go operate in the 2 Lagrangian point, which means seen from the sun, it's behind the Earth, and going around the sun with the Earth, of course. And to avoid the sun shining into the satellite, we have to rotate the satellite every 3 months by 90 degrees. This is similar to the Kepler mission. So those of you who have worked with Kepler data, you will be used to these, getting data releases every 3 months. The methods PLATO will apply from the satellite photometric data itself. It's, of course, the transit detection. But the light curves will also be used to perform astroseismology of the host stars. From astroseismology, we get precise stellar parameters, the radius, the mass, and in particular, the age. The satellite program is complemented by a ground-based follow-up program for radial-velocity observations, really involving all big telescopes to get the masses also for the smallest planets. So altogether, what we get in terms of planet parameters from PLATO will be the mean densities and the age. This sketch shows the galactic plane, or the sky in galactic coordinates. We see the galactic plane here in the center. And it's to illustrate the size of the PLATO field. The magenta field here in the northern hemisphere is the Kepler field, and you see the blue PLATO field in comparison. It is much larger than the Kepler field. The field has this flower-like appearance because the cameras on the satellite are grouped into 4 groups, which overlap in the center on the same place in the sky, but in the corners, 6 cameras observe the same field in the sky, and in the center, all 24 observe the same field in the sky. And then we have here the 2 cameras for the fine guidings, for the stable pointing of the satellite. But we will actually start in the southern field. This is driven by the fact that the best telescopes for radial velocity, the best instruments for radial velocity are in the south at the European Southern Observatory. So we will start here in the southern field. And we will cover also the test continuous viewing zones. So we will have many test targets here in our field of view as well that can be followed up with PLATO. And this, I don't want to go into details with this. I know it's on YouTube, and those of you who want to get a little bit more overview, what is in the PLATO field in terms of known candidate planets, test candidates, non-transiting planets, clusters, and so on, I recommend the publication by Nassim Bedi, who really describes the field very detailed. Now, in terms of planet sensitivity to detect planets, there have been several studies made in the recent years, and one recent one is done by Yoshi Eshin, who compared the PLATO sensitivity to a recently published sensitivity for the TESS mission, excluding the TESS extended mission. And what is shown is the planet radius over orbital period again, and the color coding shows the sensitivity for the detection of the planet. And we can see that with the PLATO mission, now looking only at 2 years, so only at the first pointing for 2 years, how we can extend and push the detection limit towards long period planets. Now you may say, okay, if you're very critical, I have an Earth radius here, and the orbital period of the Earth is 1 year. So we are still only at about 50% sensitivity here in 2 years. That's true, but that then will be a decision to be taken after launch, whether we stay longer on that field, which of course would push the sensitivity further towards longer period planets. Well, and then the big question is, how many planets will we detect? And I recommend 2 papers on this. One is the overview paper we wrote last year, but also a recent publication by Juan Cabrera, who in detail investigated the expected performance of the mission. This table gives a summary. We will detect several thousands of planets of all types and all magnitudes, but in terms of habitability, we are, of course, interested in this in the lower line that are the bright planets orbiting bright stars, bright, so we get the masses, and small, less than 2 Earth radii, around solar-like stars. And you can see our estimate. And it ranges from 0 to 120. Why is that? Because the point is to give a number of expected planets, we have to put in an assumption of how many stars have a planet like the Earth. So we have to put in an assumption, and depending on which assumption we put in, we get an answer. If we assume that only 2% of the stars have an Earth-like planets, our detection will be zero. But if we assume almost every star, 60-80% of the stars have an Earth-like planet in the habitable zone, we will actually detect a large number. So I don't know what's the truth. We have to wait. This is the white spot, the parameter range. PLATO is designed to constrain this number that then can also go into the design and into the concept for future missions following these up. The other parameter PLATO is looking at is the age. And you may ask yourself, why do you need a precise age? You can talk to people studying gas planet evolution. They also need the ages. But here in this talk, talking to the astrobiology community, I want to be honest. I actually said 10% of the age based on this plot. Why? Well, the only planet we know that has life is the Earth. And if you look at the evolution of the Earth's atmosphere here shown in this plot, you see the Earth's atmosphere composition changed over the time. It changed over billions of years. But it didn't only change continuously, like the CO2 content, for example, here decreasing continuously. It also showed jumps, the increase of the oxygen, the decrease of methane. So there are certain jumps, really changes on short terms happening in the atmosphere of Earth. Well, of course, we don't live long enough to observe the evolution of a terrestrial planet over billions of years, obviously not. But we do see planetary systems in the sky with different ages. And my big vision is, and that vision is a big one, it needs PLATO and many follow-up atmosphere missions. But my big vision is if we get well-known planetary ages and we get a good statistics of small planets of known ages at different stages here during their evolution, we can compare it to that plot. We can see if we finally get similar evolutions of rocket planets over time. Now, well, you can have a look what's the situation of planet ages these days. That's a plot that Juan Cabrera just did recently for his paper. I find it very, very intriguing. First, we see that most planets are on the main sequence. Most stars are on the main sequence, so we see a big population here. But you see the lines, these lines indicate the error bars on the ages, and clearly the ages of stars, of normal field stars, are not very constrained. And just for illustration, don't get it too precise here in the numbers, but just for illustration, I put in here the approximate error bar we are expecting from PLATO. That hopefully will help us to sort this according to ages. And find out typical evolutions of planets. Now, how is that done? As I said, this is done by asteroseismology from photometric light curves. The asteroseismology analyzes the eigenfrequency of the stars, and in combination with stellar evolution models, we can derive stellar parameters and the age. Many studies have been done what PLATO can deliver, and if we can actually meet our requirement of 10% of age for solar-like stars, That has been confirmed. The plot here shows a comparison. It shows how the number of stars for which we can do this analysis increases with increasing observing time, and in comparison with the Kepler mission, the results will be similar, but we will get 80 times more stars with astroseismic results for 2 fields in 2 years, I should say. This means not only host stars, but these stars where we have astroseismic parameters, they will then be used to calibrate more classical methods. So we will get more precise ages also for stars where astroseismology cannot be done directly, for example, because they are too faint. Well, what's the next step going beyond PLATO? Of course, what we want to do finally is to have the atmosphere composition of planets, in particular of Earth-like exoplanets, as shown here in this illustration. Well, I thought about summarizing the situation where we are. Then you have to look at the TRAPPIST system. For those who don't know the TRAPPIST system, it's a planetary system with 7 rocky planets, 3 of them orbiting in the habitable zone of a cool M star. This plot compares it to our solar system to show just the size of the system. It would fit well into Mercury's orbit if you would place it in our solar system, because the habitable zone for M stars is so close to the star. This is still fine. And here are spectra taken by the James Webb Telescope by different people from the planets in the TRAPPIST system. The most interesting one, of course, TRAPPIST-E, the inner edge of the habitable zone. And to summarize this in words, so far no planet atmosphere could be detected in any one of those. The TRAPPIST-E observational program is not completed yet. There will be more data coming, but so far we could not have there have not been secure atmosphere signatures. And well, that's a bit disappointing. Again, the problem is we are looking at faint stars. We do need the detection of transiting planets around brighter stars. And this plot is showing the situation where we are in terms of space missions. We are now here, 2026, 2027. As I said, the next mission that's going up is PLATO. PLATO is exoplanet populations, populations of well-characterized planets for mass, radius, and age. There will be the Roman telescope launched later this year. Roman will perform microlensing and also include an exoplanet program. The microlensing method, I've not talked about this in this detail, but the microlensing method will not give us precise planet parameters, but it will give us a huge statistics, which will be very, very valuable for this, for statistical in comparison to planet formation models. The Chinese Earth-2 satellite will also perform transiting planets, but in a magnitude range that's similar to the Kepler mission. So Earth 2.0 will point to the north, will provide with a larger field of view than Kepler, but a similar magnitude range. So, and the next step forward then is going to atmospheric diversity with Ariel, followed by missions like the Habitable World Observatory or the European Life Concept, aiming at atmospheres of rocky planets and even biosignatures. And for PLATO, what can PLATO provide for these atmospheric missions? Well, this plot here shows the PLATO field, including targets of the Ariel mission. So these are targets that Ariel can follow up, James Webb can follow up, and Ariel and James Webb will have these targets already characterized with precise parameters from PLATO, and then performs the atmospheric study. And the remark is also that the target catalog of the criteria for the target catalog of PLATO match very well with the planned Habitable World Observatory. So when the HWO flies, then for the targets which are in the PLATO field, there will be pre-characterized planets for mean densities and ages already available. So I like to conclude with this slide. Usually I conclude talks with results, but this talk has shown you more or less where are we in the situation today in terms of rocky transiting exoplanets. And you may say, well, we want to more. And what we would like to know in particular is to understand which planets are habitable and how they evolve with time. And this picture really illustrates my big vision. My big vision here, when PLATO comes, Ariel is launched, habitable world, observability, and life. In the next decades, we will be able to address these questions. What is a typical rocky planets? What are habitable conditions, and how does it change? How does it change with planet ages and the evolution of the stellar environment? So I think we can look forward into a great future for exoplanet sciences with all these missions coming up. And well, you should ask somebody in 20 years, 30 years to give the same talk again and look back and tell us about what we really found and if that meets the predictions that we have today. Thank you very much.